Hello everyone, welcome to the NPTEL online certification course on fundamentals of food process engineering. We will start today a new topic on size reduction. This is a very important unit operation in food as well as in the chemical engineering industries. We will cover the introduction about size reduction, particle size distribution, energy requirement in size reduction, types of size reduction equipments, crushers, grinders and ultra fine grinders, cutting and slicing machine, homogenizer for the liquid food. Okay. So, since size reduction can be applied to both solid and liquid material, although we will cover in very much detail the size reduction related to solid particles, and also we will see the homogenizer, which is specifically used for making fractions of liquid particles when we try to try to prepare a liquid emulsion kind of operations. Those are also very important in some food application. So, let us see what are the introduction or the requirement of size reduction unit operation in food industry. Size reduction or comminution is the unit operation in which the average size of the solid pieces of the food is reduced by the application of grinding, compression or impact forces. Now, there are different forces that we use to reduce the size of the particle from the bigger one to the smaller one, and we will see that in most of the time these different forces not alone works in a particular operation. The combination of more than one type of operation or forces may work on the particle. Okay. And there are different kind of operation like cutting, chopping, grinding, milling, or all are used in certain kind of size reduction operation. Similarly, for the liquid and semi solid, like when we want to do atomizing or we want to do homogenizing applications, meshing, etc. So, one such example we can observe here, that is the coffee bean to coffee powder preparation. This is done by grinding to increase the surface area, that is one operation, and there are other operations that we will see. The basic objective of this is accelerating the heat and mass transfer. So, what happened that when we grind a particle, for example, coffee bean here for preparation and extraction. Now, what happened that in extraction what we are doing is, when we have extraction, we need a solvent and we need a solid micella or particles from which we want to extract the bioactive compounds. Okay. So, in that case we have a continuous solvent, and in that we have different particle, smaller or bigger. Okay. Now, as much as the interface area, that means the contact between a particle and the surrounding solvent, we can increase, so the extraction will be faster. Okay. Similarly, if you want to perform certain drying operation where we finally need some powdered form of material. So, if we grind it and then it is exposed to the heat source. So, what happened that heat can penetrate faster into the center of the material, and also the moisture can transform faster from the inner core to the surface. So, grinding in a way is resulting the increase in the surface area and thereby helping certain other operation like heat transfer, mass transfer, etc. Another is that to facilitate separation processes. For example, milling wheat to obtain floor and bran separately, okay, or filleting of fish. Now, what happened that when we want to separate the bran from the wheat kernel, or similarly we want this kind of operation in separation of the rice bran also, okay. So, in this case we want to separate two different part of a grain which is having somehow different composition or they have different use. For example, we separate the rice bran to extract the oil from the rice bran, okay. So, that is why we need the rice bran separated from the kernel, okay. So, all this operation, that is to facilitate the separation process, sometime we need to use the milling or size reduction operations. And suppose in the filleting of fish, that means we want to develop certain special kind of product of fish muscle where we want to separate the bones from the fish. So, we are doing the filleting. So, these are the special requirement of different food processing sections. Then facilitating mixing and dispersion, okay. For example, milling or crushing ingredients for dry mixing. Now, if the bigger size of particle we are using and two different spice mix, for example, we want to prepare, so then if the particle size are bigger, so mixing will not be proper and a non homogeneous structure will be there, and when we want to use is that mixture into food. So, what happened that we will have trouble in optimizing the quantity of the mixture. So, you might have seen that nowadays very ready made spice mix are coming, different branded company for the noodles making company. So, they are giving that particular kind of spice mix, okay. So, they are drying and grinding different 2, 3, 4 and more than that different spices, and then they mix them together and then they use it in certain applications. And another is to obtain the pieces and particle of defined shapes and sizes also. Now, what is that? If we consider the different shapes, then different operations are there where we need a particular kind of, let us say, spherical shape or a particular kind of structure. Then we want to grind it and sieve it in those particular kind of predetermined perforated screens, so that we can get the particular shape. Or else if we want to determine the different size fraction, for example, in the wheat milling we want different fraction of it. For example, we want suji which is one fraction, and we want the whole wheat flour, that is a more finer fraction, and also we sometime need dalia which is a coarse fraction of that. So, different fraction of same grain sample when we want to use. So, that we can get out of this size reduction operation, okay. So, as I mentioned that in the food industry there are many applications. Cereal milling, which is to obtain different kind of flour. In nowadays not only the one grain sample, but multi-grain products are becoming more and more important in terms of consumer preference, because many grain if we mix, we are getting multivitamins and mineral rich products, okay. For example, the multigrain flour is used for chapati making, okay. They are different atta sample are prepared out of that, bread sample are prepared out of that, okay. So, cereal grains to obtain flour, this is one of very important application. Then flaking of soybean prior to solvent extraction. So, not only soybean, if we want to extract any other, for example, rice bran or any other oil extraction. So, some optimized size we need to prepare, because if we make a bigger size flakes. So, extraction will not be efficient since the heat and mass transfer will not be that much efficient, right. So, for that this flaking is done, and after that the proper size reduction of those flakes is important. So, this is one operation. Then cutting of vegetable and fruit to desired shape. So, this is of course done for the preparation of different recipe, and cutting of paneer, cheese, etc., in desired shape. So, this is also one type of operation that we we are reducing the size. Fine meshing of baby food, because they do not have the the teeth for chewing all those to reduce the size. So, we need to finely mash them, and for preparation of that the companies which are going to prepare baby food kind of product, they do it by proper size reduction. Okay. So, these are the commercial application. Then homogenization of milk and cream, because you know that if you take the raw milk and boil it, so you will get the cream separated from the milk. Okay. So, the cream, because of the lighter, they come and float on the surface. Now, when we want to sell the milk or we want to pasteurize the milk, so in the milk processing plant, we need to homogenize the milk and the cream properly. So, here the this is a kind of liquid particle reduction and mixing properly. So, there we apply the homogenization. Now, size reduction mechanism in solids. So, definitely in the solid and liquid, the method by which we, or the mechanism by which we reduce the size will be different. So, first we will see the mechanism in the solid sample. One force that we apply for reducing the size in the solid is compression, where particle disintegration by two rigid forces. Compression is used for the coarse reduction in size of brittle hard materials, and compressive forces tend to produce relatively few fines. Okay. So, compressive, generally we are getting a large particle, bigger size particle out of that. Next is the impact force. So, particle concussion by a single rigid force is impact, that we do by forcing a heavier impact on a particle. So, this is kind of a unidirectional force. When material subjected to a sudden blow of force in excess of its strength, then it will fail. So, like cracking of nut with the help of hammer. If you have seen that in cashew nut processing also different research is going on to develop the sheller, okay, cashew nut sheller by mechanical means, but normally if you go to the villages where large scale cashew production is there, you will see that they do the hammering at a particular angle at the junction of the two shell to break it. Okay. So, they will blow it in every blow, they will break the shell of the cashew nut. So, this is the mechanism by which they operate it. So, impaction is relevant to coarse, medium and fine reduction of the hard material. Okay. So, there are many applications of this impact force, we will discuss them. Then another is the shear. So, produced by a fluid or by particle interaction. Okay. Then size reduction mechanism is attrition. Attrition arising from particle scraping against one another or against a rigid surface. Attrition tends to produces very small particle from softer material. Cutting, which is accomplished by forcing a sharp edged knife through the material, and this is used to produce definite size and shape from tough, ductile and softer materials. So, if you see the force and the principle and also the equipment where these forces are being used. So, compressive force, this is used in the nutcracker, the method is crushing rolls. Impact, this is used in the hammer mills. Attrition force is used in the disc attrition mill. Then there is cutting, this is used in rotary knife cutter, the mechanism is like scissors. Okay. So, these are the different forces that is used for size reduction in the solid material. Now, when we discuss the particulate solid, the problem is that when we deal with the fluid material, we consider them as a bulk fluid flow, and it is very little bit easy to understand the behavior. We can categorize them in the Newtonian or non-Newtonian fluid, and then we can calculate easily what will be the velocity and what is the shear force acting at different location. Okay. So, when we use the bulk fluid, we even assume that the uniformity in the material is existing. Okay. But when we deal with the solid material, okay, particulate solid material especially, so these are having a very complicated system. So, to defining them in a uniform way is a challenge, and most of the cases if you look into the food industry where we handle the bulk particulate solid, for example, any flour mill, okay, or any kind of processing where bulk material, dry material flow is involved. Okay. For example, before extrusion also sometimes we want mixing of different kind of raw grain sample or powdered sample, then we mix it and then we send it to the some other channel. So, that time the challenges we face, because the particulate solids are generally a complicated system than fluid, as I mentioned, because of the complex geometrical arrangements they possess, and also because of the basic problem in defining them completely in terms of the physical state of the material. The problem is that there are many irregularities in the particulate solids in their shape, their sizes and their uniformity, because sometimes they may form a clump, sometimes there will be a porous structure where lot many air pockets are there. Okay. And obviously, the size and shape non-uniformity is a major concern. So, all these are there. Therefore, the characteristics of an individual particle, if we want to express based on certain criteria, so that is important first. So, once we see that how we can define a single particulate solid, then we will move on to the different size reduction operation. So, first we will see now that how we can define the particulate solid in terms of what parameters, then how those parameters are categorized and they will be classified in different category, and then we will see that what are the actions or mechanism we can apply on them. So, to characterize an individual particle, first is composition. So, this is very essential. Okay. So, composition is the first important thing. Okay. So, this affects the density and conductivity of a material. So, composition, if it is of one grain particle, so it will have a uniform characteristics. If it is a mixture of different grain, so its composition will vary. So, therefore, the composition is one important thing that affect the density of the product and also the conductivity of the product. Suppose in terms of thermal conductivity or heat transfer as well, if you have a different kind of mixture and there are fat, protein, carbohydrate and different kind of material. So, then for each of the different kind of material, the properties will be different, right. So, first this is important. So, the particle is completely uniform or porous, or it may consist of a continuous matrix in which small particles of a second material is distributed. So, what is the characteristics that we need to know first? Second is the size. So, size affects the property such as surface per unit volume. This is very important because the surface area, if we are getting bigger surface area or larger surface area for a small unit volume, then obviously the transfer processes will be increased. So, therefore, surface per unit volume, this we can get the idea from the size, and the rate at which the particle will settle in a fluid. So, all such depend on the size of the particle. Now, the last thing is shape. Okay. Now, how this shape plays an important role? What happened that in a particulate solid, you will get regular shape of the particle and irregular shape of the particle. Now, it is very easy for a scientist to identify or to categorize the regular size of particle. For example, if we take a crystal tube, or if we take the spherical particle, round shaped particle. Okay. So, regular particle, if it is there in the bulk solid, so then to categorize them or to apply different forces or to analyze their behavior becomes a bit easy. Now, if those are irregular shape, then to handle their irregularity becomes a challenge, and then what we do is we try to define this irregularity with some kind of regular material. We replace this irregular material and we define certain kind of factor which correlates the irregular with the regular particle, and we take those regular particle size and take them in modeling of the phenomena, because any particle characteristic or bulk solid flow behavior when we want to analyze. So, we need the regular shaped particle, okay, and then we use them in the modeling. So, all those irregularities are there, we need to relate that how much they are close to a regular shaped particle. Okay. So, therefore, the shape of the particle is also very important, and once we know all these three, it is easy then to identify the particle behavior. So, bulk solid in industrial scale, when we want to analyze, now we have learned that what is the basis of a characterization of a single particle, that we have learned now based on composition, their size and the shape. Now, again the problem is we can't get one size in a bulk mixture. Okay. So, we need to transform our analysis from the particle size to the distribution of particle sizes, because when we try to handle the solids in the bulk scale or industrial scale, we can't get uniform particle size. There are very rare operation where we can get this uniform particle size. Mostly a range of particle size we can get, in that fraction of each size are present, and maybe they are dominated by one or two major size fractions. So, particle size to distribution of particle size then we need to do in the mixture, and to define a mean size which represent the behavior of the particulate mass on the whole. So, we need to develop a mean size out of all the lot of the bulk sample. We need to identify this, and further this mean size we will take a representative of all this bulk solid and do the any kind of analysis, whether we want to analyze the energy requirement for the comminution process, or we want to do any kind of bulk flow modeling. So, it is frequently necessary to reduce the size of the particle, or alternatively to form them into aggregate or sinter. So, these are the operations we may require in industrial scale. It may be necessary to mix 2 or more solids, and also their fraction, size and shape is defined in most of the cases. Okay. For example, I have discussed the concept of instantization in the drawing. So, instantization, in that we need to have a particular site. So that when that the particles are dipped into the liquid where they should mix properly. So, they will not form a clump or agglomerate, and they will uniformly dissolve in that. So, for that in instantization it happened that after spray drying also we form certain kind of size increasing operation or little bit of lump formation, so that the particular size, that optimized size that we want can be produced. So, those are the different operations that we need. Now, there may be a requirement to separate a mixture into its components or according to the size of the particle. And finally, the interaction between the particle and the surrounding fluid. So, that is a case of extraction, as I mentioned. Extraction is very much important nowadays. We try to extract many important bioactive and compound or heat sensitive compound out of the matrix. Okay. So, therefore, we can use them. And one more thing, I think we will mention it somewhere, that I would like to tell at this point, that all the grinding operation that we perform has different requirement, right. Now, if we try to produce the particle which are very much heat sensitive, where we are producing some kind of particle fractions or want to extract certain component which is very much heat sensitive. So, in that there are different operation to perform this size reduction under different temperature condition as well. Okay. So, particle characterization, single particle, we want to make it into the most common and most useful shape. So, that is the sphere, right. So, why we use sphere most commonly? Because of its symmetrical structure. Sphere is from the all side it is same. So, there is no problem of orientation in the bulk fluid or in the heat ambient or in the liquid mixture. So, that if from the every side the analysis can be uniformly done. So, sphere is the most common shape we try to assume in this kind of bulk fluid material, and the size of a particle of irregular shape is defined in terms of the size of an equivalent sphere. So, whatever irregularities we found, as I mentioned, that we relate them with the known regular shape, that is the sphere. Some important size of the equivalent sphere. So, these are these are represented as the sphere of the same volume as that of the particle, okay, or the sphere of the same surface area as that of the particle. That means, we are having an irregular particle, okay, we are having an irregular particle, we measure the surface area of the irregular shaped particle, and then the same area sphere we take a sphere which is having the same area, and the diameter of that we will take as the equivalent diameter. Similarly, there may be sphere of the same surface area per unit volume of the particle, or maybe the projected area of the particle to a plane perpendicular to its direction of motion. Okay. So, suppose there is a flow and there is a particle. So, flow past this particle is going. So, in the direction of the flow we take the projected area of this, okay, and then that we will take as a that diameter of that we will take, or the distance between the two point, in that the tangential point we will take and then we will measure the diameter, or else we will also do that the particle should pass through the same size of the square aperture as the particle, and also settling velocity as a particle in a specified fluid. So, all such are different expression of the equivalent diameter, and the size of an irregular shape is also expressed. This is kind of a tabulated form. All those things that we have just discussed, that based on surface area, based on sieve opening, based on projected area, this can be categorized under different category like sieve diameter, surface diameter having the same surface area, surface to volume diameter which is also called the sorter diameter having the same surface to volume ratio, laser diameter like having the same interaction or the diffraction pattern with the lesser beam. Okay. So, irregular shape particle which is having the diffraction pattern, similar diffraction pattern having a spherical shape is taken here and the equivalent diameter is taken. Stokes diameter which is of equal density falling at the same Stokes terminal velocity of a in a given fluid. So, all such diameters are used for analysis of the particle size. Now, one common expression is sometimes used, that is called the Ferret's statistical diameter, which is the mean distance apart of two parallel lines which are tangential to the particle, okay, in an arbitrary fixed direction. So, these are the two parallel line which are tangential to the particle, and this is irrespective of orientation of each particle coming up in the inspection. So, the orientation may change at any time, but we will take the two tangential parallel lines and take the diameter which is called the Ferret's diameter. Now, as I have mentioned that we take the common shape of a sphere and try to relate the particle with that, try to relate the irregular shaped particle with that. So, that relation is developed by sphericity. Okay. That relation is developed by sphericity, that is nothing but the surface area of a sphere of same volume of a particle to the surface area of the particle. Okay. Surface area of a sphere having the same volume as of the particle divided by the surface area of the actual particle that we are taking. So, this will define the sphericity of the particle. So, we will stop here and we will continue in the next class. Thank you.